It is chapter 14, partial derivatives. For functions of several variables, partial derivatives are derivatives along the coordinate directions. This chapter is an expansion of differentiation which you learned from Calculus 1. Here we have section 14.1, functions of several variables. We'll begin with functions of two variables. A function of two variables, f, is a rule of function that assigns each ordered pair of real numbers xy in D, a unique real number denoted by f of xy. D is the domain, and the range is defined to be the set of values that f takes on. You learned a function in this way. If y is f of x, then for each x in domain, f assigns a unique number. If it assigns more than one, then it is not a function. You learn a function in this way. Now, for a function of two variables, we may write in this way: z equal f of xy. Now, for each ordered pair of numbers, f assigned a unique number. Then it is a function defined on the domain. F is a function of two variables, and we write in this way. Then x and y are called independent variables, exactly as for the usual function that is independent variable and y is dependent variable. For a function of two variables, x and y are independent variables, and z is the dependent variable. It's a quite simple expansion. Okay, f of xy is defined in this way. Evaluate f32 and give its domain. Here means that we try to collect all the points where the function is defined. Okay, first we try to evaluate the value f32. That means x is 3, y equal 2. So that here we have that one is 3 plus 2 plus 1 over x is 3 minus 1. So top is square root of 6, bottom is 2. That's it. Now for domain, okay, first of all, inside of the radical should be non-negative, which means x plus y plus 1 must be non-negative, and denominator must not be 0. So x minus 1 is non-zero. From here, we can rewrite this one in this way. Y is larger than or equal to minus x minus 1, and x is not 1. Okay, so this is the domain. We can visualize the domain in xy coordinates. That is y direction, this is x direction. Now, y equal minus x minus 1, that one is this one, right? That is y equal minus x minus 1. Y is larger than or equal to this one, means a proportion here. Now, x should not be 1, which means at 1 here, we have to exclude this vertical line from the domain. Okay? So we visualized the domain here. Find the domain of the function. Okay. F of xy is x times logarithm y squared minus x. Logarithm, natural logarithm, accepts only positive values, so that y squared minus x must be positive, which means that that's y squared is larger than x. Pictorially, you can make this one. Y squared equal x has this graph, such type, and x is y squared is larger, and so that this direction, right? Okay. Find the domain and the range of the function. And inside radical, 9 minus x squared minus y squared must be non-negative, which means that x squared plus y squared must be less than or equal to 9. That one is the disk of radius 3. The origin is the center. Okay. And that is the domain. So pictorially, we have here a disk of radius 3. Okay, inside here. Okay. Now, to find the range, we have to collect the function values. Now, this one is always non-negative, and in any case, this 9 minus x squared minus y squared cannot be larger than 9. So it's bounded by 9. And when x and y are 0, the origin, the value is 9. And as xy moves far away from the origin, the value becomes smaller, and along the boundary, the value must be 0. Okay, so f must be non-negative, and the function square root of this one must be bounded by square root of 9, which is 3. So that's the range. Okay. If f is a function of two variables with a domain D, then the graph of f is a set of all points such that z is f of xy for all xy in D. For standard function you learned from calculus 1, for that one, the graph is now the collection of x and y, and here x is inside of D. Right? That is the graph. Okay, so we can write in this way. The exactly same way for graph of functions, a function of two variables. Now this is from domain, and this is from the range, so that all collection of all these points is the graph. So it makes a surface in 3D space. This makes a curve in two-dimensional space in xy coordinates. And now this one makes a surface in xyz coordinates. Okay. Let's try to sketch the graph of this function. Now, in order to do that easily, rather than using f of xy, we may try to use z. So we reach at that one. It means we try to show the function value in z direction, vertical direction, if xy are in horizontal direction. We rearrange this one in this way. Then from here, we can find easily intercepts. For example, if x and y equals 0, which means it's in z direction. So that is in z direction, we try to find intercepts with the z-axis, then z must be 6. How about y? In y-intercept, there must be x and z must be 0. Then from here, y must be 3. Now how about x-intercept? Then y and z must be 0. Then yz are 0, then x must be 2. So once we start with 3D coordinate, okay, there is x direction, there's y direction, and this is the z direction. Then x-intercept is 2, and y-intercept is 3, and z-intercept is 6. If we draw triangle connecting these 3 points, then the graph is plane, including this triangle. Okay. Now sketch the graph of g of xy as square root of 9 minus x squared minus y squared. Okay. You can sketch the graph by using the method of traces. You learned this one in preliminaries. You can do that. Now, rather than that, you may sketch the graph more easily in this way. Rather than g of xy, we are using z, and we reach that equation. We square, then z squared as that inside the radical, and move x squared and y squared the other side. So we reach at here x squared plus y squared plus z squared is 9. From the original one, z is non-negative. So we can conclude that the graph is upper hemisphere. You can draw the graph yourself. The level curves of a function of 2 variables are the curves with equations f of xy equals k. Now, k must be chosen from the range of f. So if k is outside the range, then the equality is not satisfied, so that the level curve must be empty. Look at here. The surface, the graph of a function is given in this way. Then if you try to cut the surface with a horizontal plane, in fact, you can consider this one in this way. This is z equal f of xy. That is the graph of a function, and z equal k. That is a horizontal plane. So intersection between these two will be a level curve. So practically, from this graph, we try to use horizontal plane and cut the graph. Then you can see such contours. So once it is depicted on XY plane, then that is level curves. Okay, this one, as you may saw this one, which is a topographic map of mountain, and so that you can see the same height curves. Okay. Sketch the level curves of f of xy as 6 minus 3x minus 2y for k chosen in this way. I'm sorry. Okay, now from the definition, level curves are given in this way. 6 minus 3x minus 2y equal k. Now k will be chosen from here. That is definition. Mathematics always start with definition. Okay, when k is minus x, then we have that here. There's a minus x, so that will be moved here to be, okay, we rewrite this one in this way. K, no, okay. 6 minus k equal, now 3x plus 2y. Okay? Okay, then once k is minus x, then that's 12 equal 3x plus 2y. You may write this one in this way. Move again this one to the other side and divide by 2, so that y equal minus, okay, 3 over 2x and divided 2, so that is a 6. How about k equal 0? Then now k equals 0, so that is 6 equal the same. And from here you can get that is the same term, and 6 is divided by 2, so we have here now 3. The same way, now k equals 6, then that will be 0 and equal the same term. So from here, y equal that same term, and here that will be 0. Okay, and now from this one, along with that pattern, you can conclude when k is 12, then we have here y equal this linear term minus 3. You can see quite easily. And for each level curve, we can make here the graph. Okay. Now from this one, the slope and negative and plus x, so there is passing point here. So that one is plus x. And that is now when k is minus x. And here 3, parallel, that is, okay, when k is 0. Now, another one we have here, that is when k is, oops, that is minus, k is minus 6, so there's k is 6, and k is 12, then we have one more line here. So the level curves are straight lines for the function. Okay. Sketch the level curves of g of xy equals square root of 9 minus x squared minus y squared. Okay. And now we choose k is 0, 1, 2, 3. level curves. From definition, that is square root of 9 minus x squared minus y squared, which is k. Okay, from here, square and manipulate, then, okay, 9 minus x squared minus y squared equal k squared. So that from this one, x squared plus y squared equal 9 minus k squared. So from here now, k is 0 and 1 and 2 and 3. So once, so right side, once k is 0, that is 9 when k is 0, and that is 8 when k is 1, that is 5 when k is 2, and that must be 0 when k is 3. For each of these numbers, that will make a circle radius of square root of these numbers, so that you can easily sketch the level curves, right? For this case, we have now the circle of radius of 3. Okay, so that there's when k is 0, and when k is 3, then x squared plus y squared is 0, so that will make it just a single point. So that is when k is 3. Okay. Okay. You can sketch level curves by using computer algebra system. Here for the function, here the level curves are made, and by using computer programs, you can see quite easily, and rather than detail case by case the manipulation, you can get the output quite easily. So that's the reason we are trying to use computer algebra systems. Okay. Here we have an example. Now the function is defined to be minus xy e to the minus x squared minus y squared. This is a Maple code, and Maple requires importing the packages. So by using with command, you can do that. Plots and also vector calculus packages are included, and f is defined in this way. Now b is used to determine the domain. Now x is moving from minus 3 to 3, y is moving from minus 3 to 3, and contour plot in 3D is made in this way. And here that one is made on 3D along the graph, and now that is a real contour. These are projected onto XY plane. From definition, the level curves are on two-dimensional space, so contours. To get graph, you may use various packages, Mathematica, Maple, MathTalent, whatever convenient you can use to get graphs and to get plots. Okay, here, functions of 3 or more variables. We learned how to deal with functions of 2 variables. Now, let's move on for functions of 3 variables. That is, the manner is exactly the same, but now we are dealing with 3 independent variables rather than 2. A function of 3 variables, f is a rule, again, is a function that assigns each ordered pair of real numbers, x, y, z, in a set D. Of course, D is the domain, a unique real number denoted by f of x, y, z. So once we try to write down the range, then we may start with, for example, by introducing another variable, dependent variable, that is, for example, w as f of x, y, z. So in this way, we try to indicate the dependent variable. Okay. Find the domain of f once f is defined in this way. Okay. For this one, now logarithm accepts only positive numbers. So z minus y must be positive for this portion. For every x, y, z is well defined. Okay, so the domain should satisfy this one. So z is larger than y. That determines the domain in x, y, z coordinates. X, y, z. Now z is larger than y. Okay, here we consider a plane, and in zy plane and 45-degree angle, consider a plane like that. Oops. Okay, let's try to draw again the sketch line like that. So consider a plane including this line and now parallel to x-axis. So that's plane, and z is larger than y, so upper portion of this hyperplane is the domain of the function. We learned the level curves. Now level surfaces are defined in this way. Function f of x, y, z equal k. Earlier for level curves, f of x, y equal k. Now for this function, we try to get, we define level surfaces in this way. So just that is a simple expansion of level curves. Because this makes curve, we say level curves. Now this makes surfaces, so that we call level surfaces, but the idea is basically the same. Okay. Now for the function level surfaces, from this definition, we can write in this way: x squared plus y squared plus z squared equal k. These are level surfaces, so that we may write this one in this way: square root of square root of k and squared. That means that the level surfaces are the sphere radius square root of k for given k. So for each k, we can make here the level surface. That is now sphere of radius square root of k, right? For these surfaces, okay, we start with a point on the surface. If you try to measure function value, then along the surface, the function value is all the same. In fact, the level surfaces mean that it's collection of points so that the function value is the same. So along the surface, the function value is always the same as k. So that in that direction, and the function value may not change or even change very small. But if you consider the normal direction, then the function value will change. In fact, the orthonormal direction is the direction that changes the function value fastest. In fact, the orthonormal direction is the fastest increasing direction of the function value. We'll use this observation later on when we deal with optimization and maximum and minimum values of a given function. Okay? Okay, this is the end of the section. Thank you.